My name is John Rogers, and I'm on the faculty here at Northwestern University with appointments in materials science and engineering, biomedical engineering, and medicine. I'm working in a field known as bioelectronics, an area of research that involves the development of semiconductor device technologies that are intrinsically biocompatible, designed as tools to advance biomedical research and as systems to improve patient care. When the Berlin Wall fell, I was just starting as a first-year PhD student at MIT, and I heard about this powerful news while in my dorm room at Ashdown House. My research breaks down the wall that currently exists between common consumer electronics gadgetry with their conventional rigid, planar forms and invariant physical properties, and living organisms with their soft curvilinear features and time-evolving characteristics. Put simply, the challenge is in achieving electronic devices that resemble biology, to blur the distinction between the two in a way that leads to profound beneficial consequences in areas ranging from neuroscience research to clinical health care. Our solution exploits new classes of electronic materials in ultra-thin films heterogeneously integrated together with elastomeric materials in unusual device architectures that can bend, stretch, fold, and twist, and in some cases even slowly dissolve away in the body to allow intimate integration with soft tissues of living organisms over long periods of time without adverse reaction. A key specific focus of direct societal benefit is to improve the technologies used to monitor key vital signs in vulnerable populations, with an emphasis on maternal, fetal, neonatal, and pediatric patients. An example is in thin, flexible, or skin-like wireless devices to track health parameters associated with premature babies in neonatal intensive care units as replacements for the costly, invasive wired systems used currently. The result allows freedom of movement of the babies and more frequent skin-to-skin interactions with parents, with known therapeutic benefit to the development at these earliest stages of life. Now, with regulatory approvals, we have successfully deployed these technologies in pilot trials across key hospitals, not only here in the United States, Canada, and Europe, through commercial partnerships, but also into several lower and middle income countries, including Zambia, Kenya, Ghana, India, Pakistan, and Mexico, via philanthropic support. A question that remains unanswered is how these technologies might form new standards of care based on a wide breadth of physiological metrics beyond parameters measured today. I lie awake at night thinking about how to accelerate the translation of these advances into practical technologies for use at scale. My hope for the future is that these technologies will be available to all patients in need at any location across the globe, saving and improving lives.